So for this problem, we have a cooling tower with hot water flowing through the top of the cooling tower and exiting cooled at the bottom, with air being blown up through the bottom of the cooling tower and exiting slightly warmer up through the top. So for this problem, we want to derive some differential equations for the change in position, temperature of the gas phase, and temperature of the liquid phase with respect to position. So in this cooling tower, I'm going to define position as Z, and I'm going to say that as you go down the cooling tower, Z is increasing. Also in this cooling tower is some packing material, and the specific area, lowercase a, is defined as the surface area in square meters per cubic meter of the cooling tower. A section of this tower can be taken, and this is infinitely small, and I'm going to call this dz, which will give us our position term in a lot of our equations. And then the area of a cross-section of the cooling tower will be expressed as uppercase A. So I will also define Y, which is mole fraction, as the mole fraction of liquid water of water vapor in the gas phase. So the first differential equation that we're going to derive is how the mole fraction of water in the gas phase is changing with time. Or not with time, with position. So the first thing that I want to do is to define the flow rate of the gas phase. So I'm going to say that the flow rate of the gas phase is going to be uppercase G. And I'm also going to define this in terms of meters squared seconds. So I'm going to say that the flow rate of the gas phase is per square meter per second. So we're going to say this is kilograms per meter squared seconds. And we know that this gas flow rate is equal to the gas flow rate of water vapor plus the gas flow rate of air. So when looking at the change in mole fraction, we know that the total gas flow rate divided by the molecular weight gives us moles per meter squared seconds. And when we multiply this by the mole fraction of water, we get GW, which is the flow rate of the vapor water in the gas phase. So we're looking for how the mole fraction changes over time. So I'm going to take the derivative of this side, and I'm going to set this equal to the right side of the equation that we're going to take a look at now. So we know that this is in moles per meter squared seconds. So we need to look at what this needs to be on this side. So I'm going to multiply each side. I'm going to multiply this side by the area, since this isn't moles per meter squared seconds, to just make it moles per second. So when we're looking at this, the first thing I think of is how liquid is entering the gas phase. So how is liquid being evaporated in the gas phase? And when I think of that, I think of molar flux. So I'm going to use the equation for the molar flux. So we have the mass transfer coefficient times the concentration driving force. So we have the concentration close to the surface minus the concentration far away from the surface. So after we've done this is also in moles per meter squared seconds. So I'm going to multiply this side by the area as well. And the area terms cancel out. And then we want the change in mole fraction with respect to position. So I'm going to multiply this by dz in order to get this with respect to position. And now we have moles per meters cubed seconds. So in order to cancel this out, I'm going to multiply that by the specific surface area A. So now we have everything in moles per second and moles per second. So when I simplify this, we could do this and use the product rule, but it will make our math really complicated when we try to take the derivative of this side using the product rule. So for simplicity, we know that the rate that water is entering the gas phase makes such a little difference in both the molecular weight and the gas flow rate. So I'm going to say that G over M is constant in this case, just to make our math a little easier. So we're going to pull that outside of the differential. So G over M times the change in mole fraction is equal to the specific surface area A times the mass transfer coefficient Kc times the concentration driving force times the change in position. And when I divide each side by dz, we get the change in mole fraction with position. So dy over dz is equal to A times the molecular weight divided by the gas flow rate times the mass transfer coefficient times the concentration at the surface minus the concentration far away from the surface. I am also going to define this term here as the molar flux of water. So the molar flux of water is equal to Kc times the concentration difference. And this right here is our differential equation for how the mole fraction is changing with respect to position. So the next thing that we're going to solve for is the change in temperature of both the gas and the liquid phases with respect to position. So I'm going to start with how the temperature of the water changes with respect to position. So in order to do this, I first need to define a new term. I'm going to call it L, and this will be the mass flow rate of the water through the column per square meter. So this will be kilograms per meter squared, and then this will also be per second. So this will be the amount of water that is flowing through a specific area per second. So after we've done this, when we're talking about change in temperature, the first thing that comes to mind is an energy balance with respect to enthalpy. So I can first solve for the enthalpy of the liquid water by saying that the mass flow rate of the liquid water times the area gives us the mass flow rate, so the kilograms of water flowing through the column per second. And then we can multiply this by the heat capacity of the liquid, Cl, and then also multiply this by the temperature of the water. So this will give us the enthalpy of the water that is flowing through the column. So in order to find the change in temperature, we need to find the change in enthalpy. So we can take the derivative of this, and we're going to assume that the area, the length, or the liquid flow rate, and the heat capacity of the water, the variability of this is so minuscule that just for simplicity in our calculations, we're going to assume that this is constant. So we can pull these out front and say that the area times the liquid flow rate times the heat capacity is constant, and the only thing that is changing is the temperature of the water. And then we're going to set this equal to the second the second side of this equation, which will be how the enthalpy is changing. So we know that the two components for the change in enthalpy of this liquid water will be the heat of vaporization, because water is evaporating from the liquid phase into the vapor phase, and then also the heat transfer of the water to the gas phase, since the water is hotter in this situation. So first of all, we have the heat of vaporization, and I'm going to multiply this by the molar flux of water, which we've already defined over here when solving for the change in mole fraction. So I'll multiply this by the molar flux of water, and then we'll also make this negative because as the water is evaporating into the gas phase, the temperature of the water is decreasing. So the evaporation will cause the temperature to decrease, so this value should be negative. And then we'll multiply this by the area of the column, and in order for the area to cancel out, we need to multiply it by the specific surface area. And then after doing that, we need to get the meters cubed in the bottom to cancel out, since we have it per volume. So we'll multiply this by the thickness of the section, which is dz. And this will also help us get everything in terms of position. So now the second component of this is the heat transfer component. So we have the heat transfer coefficient H times the temperature of the gas minus the temperature of the water. We also need to multiply all of this by the area, the specific area, and the thickness as well. So now we have all of these. The area terms cancel out, and we can solve for the change in the temperature of the water with respect to position. So the first thing that we need to do is we can factor out the dz terms of each of these terms on the right-hand side, and then divide it over here, and then move this over to the other side of the equation. So we have the change in the temperature of water with respect to position is equal to the A factors out. So we have the specific area divided by the liquid flow rate times the heat capacity of the water times the heat transfer coefficient times the temperature driving force minus the heat of vaporization times the molar flux of water. So this is our final equation for the change in the temperature of the liquid water with respect to the position in the column. So now that we have this, we're going to move on to solving for the change in the temperature of the gas phase with respect to position. So when we take a look at a cross-section of this cooling tower, we see that the enthalpy of the water going in equals the enthalpy of the water going out. So this is the enthalpy of the water going in, and then we have the enthalpy of the gas phase going out. So we have this going out. And then the total enthalpy of the system is equal to the enthalpy in minus enthalpy out. So for the top, the enthalpy of the water minus the enthalpy of the gas phase is equal to the total enthalpy. And then for the bottom, we also have the enthalpy of the water minus the enthalpy of the gas phase. So going in is the enthalpy going in is the same as the enthalpy going out. So the change in enthalpy is equal to 0. So the change in enthalpy of the water minus the change in enthalpy of the gas is equal to 0. And so therefore, the change in enthalpy of the water is equal to the change in enthalpy of the gas. Now this is very convenient because we just solved an equation for the enthalpy of the liquid phase. So we can create a similar equation for the enthalpy of the gas phase and then use that to solve for the change in temperature of the gas with respect to position. So when we look at the enthalpy of the gas going in, it's going to look very similar to this equation that we have up here. So we have the gas flow rate multiplied by the area, and we want to multiply this by the heat capacity of the gas phase, and then by the temperature of the gas. Now for this, we also want to add the enthalpy of the vaporization, since the enthalpy of the vaporization will be heating up the gas phase. So we have the enthalpy of vaporization times the gas flow rate divided by the molecular weight in order to get this in terms of moles. And then we're also going to multiply this by the mole fraction Y, because we just want the gas flow rate of the water vapor and not the air. So when we take the derivative of this will give us the change in enthalpy for the gas phase. And we can set this equal to the change in enthalpy for the liquid phase that we have up here. So I'm just going to copy down this equation right up here. So we have negative heat of vaporization times the area. So now that we have this, and this will also be multiplied by the area because the flow rate of the gas is per area. So all of these area terms will cancel out, no problem. And then we are left with the change in enthalpy of the gas phase is equal to the change in enthalpy of the liquid phase. So again, for the simplicity of calculations, we're going to assume that the gas flow rates remain the same, the molecular weights remain the same, and the heat capacity remains the same. Because the difference is just so negligible, it won't make a significant impact on the values that we get. So just for simplicity of calculation, we're going to keep these constant. So I'm going to pull this out of the differential. So we have the gas flow rate times the heat capacity times the change in temperature of the gas phase plus the heat of vaporization times the gas flow rate divided by molecular weight times the change in mole fraction. I'm also going to divide each side by the change in position in order to get these change in position. Okay, so I'm also going to copy this down right here. And I will pull out the a from each side as well. The lowercase a from each side as well. Plus H, temperature of the gas, temperature of the water. Okay, so here we have each side of this equation. And when I see this dy dz, I get really happy because we've already solved for that over here. So we can kind of plug this in, and we see that this is equal to the specific surface area times the molecular weight divided by the gas flow rate times the molar flux of the liquid phase. So I'm going to set this in right here. So we have A over M over G And okay, so we have this right here, and actually this should be negative over here. The change in mole fraction with respect to position should be negative, because as we move down the cooling tower, the mole fraction will decrease because the water is evaporating going up. So we have this plugged in. The gas flow rate cancels out, the molecular weight cancels out, and we're left with the heat of vaporization times the negative specific surface area. And then over here we have the negative heat of vaporization times the specific surface area. So these cancel out, and we're just left with this term right here. So we're left with times the molar flux. So these cancel out, and we're left with the change in the temperature of the gas phase with respect to position is equal to the specific surface area times the heat transfer coefficient divided by, these moved over to this side, so the gas flow rate times the heat capacity of the gas phase times the difference in temperature of the gas and the liquid So this is our final equation for the change in temperature of the gas phase with respect to position. And now we've derived all of the differential equations that we were looking for, and we can move into solving for the actual values of these equations with the given parameters in Google Collaboratory.